Welcome to our session. My name is Karl Dietrich. I'm from Lansing Community College.
Bill Saichek from Orange Coast College, Costa Mesa, California.
And our presentation is teaching wireless networking in your future. Who currently teaches wireless networking? Okay, so a lot of this stuff is pretty basic. It might be rudimentary. Hopefully we can point something out that you may not know. Okay, all right. Before we start, I want to give thanks to the book publishers, primarily Cengage and Cybex, which is what I use in my class, okay, which I use to study for the CWNA. I am CWNA certified. It took me 2 times to get there, but I got it. The biggest surprise was I knew the basics. It's just like math, where you know addition and subtraction and all that. Then you go sit down and, okay, here's solve 60 story problems now. And that's how the CWNA exam is set up. So it's a little bit more difficult than just answering a bunch of multiple choice questions. Okay, so wireless LANs. Been around since, mid-90s or so. The IEEE organization started working on that early 1990s, came out with the original 802.11 standard. And then down the road, we came up with the different flavors of 11B, A, G, and currently we have 802.11.N. Okay? Going back to the original 802.11 standard, it specifies that wireless transmission could take place either through infrared, and we all know where that has gone to now, or radio frequency signals that operated at a blazing speed of 2 megabits per second. So something had to be done to get those speeds up. So then what came next was the 802.11b for Bill. There we go. Okay. All right. 802.11b, which got us up to a blazing 11 megabits per second. 802.11b does run on the 2.4 gigahertz frequency band, which is part of the larger ISM band, Industry, Science, and Medicine. Separated by 22 megahertz channels. Bill's going to show a demo what that really means here in just a few minutes. Okay? And also, the signaling methodology for 802.11b is something called DSSS, which is short for Direct Sequence Spread Spectrum. And I won't go into all the gory details about that because we just don't have time to do that today, but that is kind of significant because B right now is the only standard that actually uses this. Does anybody block 802.11b on their wireless networks? So anybody that comes in with older stuff can't connect? Okay, all right, that's a very, very good thing. All right, then 802.11a was released after that. That runs on the 5 gigahertz frequency, which is part of the larger uniband. Not as congested. There's everybody does their devices, you know, cordless telephones and all types of things like that. So there's lots of devices out there that use that. 802.11b, or excuse me, A, theoretical speed 54 megabits, probably around 18 to 20 is probably where you're going to be. And the signaling technology that we use with 802.11a is OFDM, orthogonal frequency division multiplexing. And I'm going to make you say that before we let you leave the room today. All right? Okay, so now what came next was 802.11g. What they tried to do is get the best of both worlds with the speed of A with the distance of B. So that was the primary motive behind 802.11g. Also operates on the 2.4 gigahertz frequency band. Distance about 350 feet or so. And again, it also uses OFDM when it transmits the data. Okay? Currently we have 802.11n. Finally. How long did it take the IEEE organization to ratify 802.11n? 7 years. And how fast does technology move? So is everybody really mad at the IEEE organization for dragging their feet? Yeah, especially the Wi-Fi Alliance. We'll see more on them in just a couple of minutes. But anyway, the 802.11n ratified finally September 2009. A theoretical speed of 600 megabits per second. If your devices were this far apart, you probably might be able to get 600 megabits per second. That'd be about the only way you could do that. Something new and kind of the, I don't want to call it a game changer, but one of the big things with this standard was that all 802.11n devices must contain 2 radios or transceivers. That was the biggest difference, okay, with the 802.11n. You've got to have 2 radios in all of your wireless devices. So if you want to have an 802.11n device, you've got to have at least 2 radios in it, okay? 802.11n can work on 2.4 or 5, so it's backward compatible with A, B, and G. What a lot of people set their end networks up to do, they do client access on the 2.4 and then do their management backhaul then on the 5 gigahertz, all right, for those 2 frequencies. Uses the same data modulation technique, OFDM, all right. However, 802.11n does things a little bit differently. It manages frames, channels, encoding. We'll talk about that in just a couple of minutes. But what N allowed us to do was get what is called a high throughput network. So if someone says they have an HT wireless network, that means, okay, they are running true 802.11n, no A, B, or G's to slow things down. And if you're running pure 802.11n, that in HT, that is called, test question, greenfield mode, okay? So if you hear someone running their HT wireless network or it's in greenfield mode, that means they are running a true, pure 802.11n network. Okay. Another big piece with 802.11n was something called MIMO or MIMO, depending on what part of the country you're from, is how you would pronounce that. Basically, you have multiple access, or excuse me, you have an access point with multiple antennas. And each one of those antennas can send a signal. You can either group them together redundantly, or you can send separate data streams. We'll see this here in just a second. But it's still a one-to-one communication. Like the DMV, you take a number, you get in line, you wait your turn to talk to the access point. Okay, and we'll get a little more detail on that in just a couple minutes. Okay? So, some things that 802.11n can do, that MIMO can do, something called spatial diversity, where you have multiple antennas. You can send redundant signals, or the same signal through multiple antennas, so hopefully, at least one will get to the other side without being corrupted. So that's one way that we can speed it up because it reduces retransmissions. Spatial multiplexing is you take, let's say you're transmitting a file, and I want to send a file to Bell wirelessly, and I have MIMO, I can send part of the file on one antenna and the other part of the file on the other on the second antenna. So theoretically, I'm doubling my speed because I'm sending twice as much data. In real life, that doesn't happen, which we'll see in just a minute. Okay, but it can be set that way. Maximal ratio combining, if I do send redundant signals, by the time it gets to Bell, those two signals have combined into one single strong signal, okay, so which would help eliminate errors. And also transmit beamforming, which is really kind of neat. Again, I'm not going to go into the physics of it, but it allows an omnidirectional antenna, which we'll see in a minute, to actually, instead of just a flat circle, it can actually steer the data stream to a specific antenna. Don't ask me how that happens. It's all physics, and it's way out of the scope of what we're talking about here. But that was the biggest thing. One of the big things was transmit beamforming. All right, 802.11ac. Anybody actually fallen for buying pre-AC equipment? Anybody want to fess up to that? No? Okay, very good. And you'll find out why in just a minute. All right, gigabit wireless, gigabit Wi-Fi. 802.11ac is going to be a game changer. If you want to future-proof your wireless networks, okay, you need to follow the specs of 802.11ac. We'll review a few of those here over the next few slides. Okay. You can see there's some bullet points here. I'm not going to bore you to death by reading those, but the biggest one that you need to take away from this is the spectrum. 802.11ac will only run on the 5 gigahertz frequency, which means if you have 802.11g equipment, guess what's going to happen in 3 years? You're not going to be able to use it anymore. You can. It's going to be like walking into a room with 802.11b today. You're not going to be able to connect to anything. So down the road, if you want to future-proof your wireless networks, you need to get on the 5 gigahertz frequency and then put away that 2.4 gigahertz, okay? Because coming down the road, it's just going to be, won't be used for wireless networks anymore, okay? All right, this is the big game changer with 802.11ac. Not only is it MIMO, multiple input, multiple output, but you also have multi-user MIMO, which means that your access point, remember we said a minute ago, it's like with the DMV. You take a number, you get in line, you communicate, you go to the back of the line and wait your turn again. With multi-user MIMO, an access point can hold on multiple conversations simultaneously. Okay? So the one-to-one communication is not going to be there anymore. And this is where the speed's going to come from. Instead of having to go back to the end of the line to transmit, we'll see an example of that in a minute, multi-user MIMO can do simultaneous multiple transmissions with multiple clients, and that is huge. That is just huge, okay? So I was going to say with the pre-AC stuff, I don't know if they've got this down yet. I still think they're fine-tuning it, the last that I've heard. So you may want to hold off on that a little bit before you just run out and buy a bunch of AC equipment, okay? All right, is there a downside to AC? Well, yeah, the signal doesn't go very far. It's in the 5 gigahertz frequency, which means that because it's a higher frequency, the signal fades much, much faster. So in a commercial environment, if you do want to upgrade to 802.11ac, you're going to have to, I don't want to say rip out all your access points, they're all going to have to be repositioned. Okay, because if you're on the 2.4 gigahertz frequency now, because of the distance limitations with the 5 gigahertz frequency, all of your access points are going to have to be reshuffled around so that you can get proper client coverage areas. Okay? All right, speaking of access points, a couple different types. The fat access point, Bill has one in the back of the room, which he's going to let you attach to here in just a few minutes. Okay? All the management capability is in the access point itself. So if you want to manage your access point, you have to connect to that access point and make changes to it. Now, if you're in an enterprise with several hundred access points, we don't want to do that, right? Okay, we just want a central mode of communication, which is where your thin access points or light access points come from. Those are just like a wireless hub. Takes data in, passes it on. Takes data in, passes it on. That is all the thin access point does. Okay, so how do you control that thin access point if there's no knowledge in it? You have to have something called, test question, a wireless LAN controller. The drawback to that is there are no standards for wireless controllers. It's all proprietary. So if you've got a Cisco system, you're stuck with Cisco unless you rip all of it out and go with Maru or Aerohive or somebody like that. So it's a great system and it's easy to manage with the centralized controller, but it is proprietary. So you're going to be locked into a specific vendor when you make that decision. Okay? Now, does the controller need to be on site? Not anymore. Okay? Because we can use cloud management. A service provider across the world can actually manage another organization's access points, okay, through cloud management. That doesn't mean, and I know you probably heard a zillion things about cloud this week, which is great, that's fine, but one thing, remember, please, 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 the internet is not the cloud. The internet is just a communication pathway. That's all it is, all right? And there's several other sessions on clouds if you want to get more in depth on that one. But the controller can be off-site. Okay, so you've got several hundred access points throughout the building. We're going to run extension cords all through the ceiling to power those babies up? No. What we're going to use is Ethernet cable to power those access points. So there is a standard for power over Ethernet. The original standard 802.3AF provided up to 15 watts of power, give or take. Okay. But when 802.11n came around, test question, okay, what was one of the standards of operation for 802.11n about radios? You had to have 2, which means 15.4 watts wasn't going to cut it. So what the IEEE came out with is something called PoE+, which changed the standard or updated the standard to 802.3AT, which provided up to 25.5 watts of power through your Category 5 cable. Okay? All right, now that's the basics on that one. A little bit about radio signals. We've talked about hardware. Let's talk a little bit about what happens once we inject that signal into the antenna. You're going to generate a radio wave. And I don't want to get all full of physics on this, so we're going to keep it basic. 4 things you need to know, and there's going to be a test on this at the end of the day. Wavelength, frequency, amplitude, and phase. If you want to teach wireless, you really got to know those 4. Okay? All right, wavelength, all right, is the distance. Here is our wave here. Wavelength is the distance between the crest of the wave. You could measure it anywhere, but generally people measure it at the crest of the wave because it's easier that way. So that's wavelength. Then we have frequency. How often does that wave complete a cycle? So we have an example of lower frequency waves and higher frequency waves. Okay? Amplitude is the height of the crest of the signal. Okay, so we have it right here. This is the amplitude, the height of the wave. Okay? And finally, we have the phase, all right, and direction. I like to substitute direction with that. And as you can see, the frequency is the same, but the direction of the wave is a little bit different. You could, if you look at this, you could call these 2 waves are 180 degrees out of phase. Okay? All right? So we have this one is starting on the up and this one starting on the down, but they're still both running the same frequency. All right, so wavelength, amplitude, frequency, and phase. Now, we have our carrier signal. Our analog signal is a wave, but we have a whole bunch of digital 1s and 0s. So how do we get these 1s and 0s onto our wave? What's the M word? Modulation. Oh, I should have brought some candy. I didn't even think about it. Okay, so we have to modulate or do some modulation to get those ones and zeros onto our carrier wave. And we can modulate it in one of three ways. However, 802.11n uses a combination of modulation techniques to get that speed up. We can modulate the amplitude. Remember, we just talked about that. Okay. We can modulate the frequency, or we can modulate the phase of that wave. So as an example of amplitude modulation, okay, so what we have is low modulation and between these dotted lines are all time slices, usually measured in microns, pretty quick, okay? So in this time slice we have low amplitude, so that's going to be a 0. In this time slice we have high amplitude, so that's going to be a 1. So we have low, high, low, low, and so on, so we have 0, 1, 0, 0, 1, 0, 1, 1. Okay, so we've modulated the amplitude. Now you see where it says shift keying at the top? If you want to get all technical about it, okay. In analog, they call it modulation. In digital, they call it keying. But everybody just calls it modulation, so don't worry about that. Just like a cable modem's not really a modem, as everybody calls it anyway. Same thing. All right, frequency modulation. So you can see here where we have 2 cycles in this time slice and 4 in this one. So we have 2 cycles, that represents a 0, 4 cycles represents a 1. So we have 0, 1, 0, 0, 1, 0, 1, 1. Everybody with me so far? We're doing good? Okay. Now phase, this is where the students trip up at, okay? The phase, this is why I like to say direction instead of phase. If there is no change in direction of the wave in this time slice, then that represents a 0. If there is a change in direction at the beginning of that time slice, that means this time slice is a 1. So here we have no change in direction, so it's a 0. And then here we have a change in direction, so this time slice is a 1. No change is a 0, no change is a 0. Then we have another phase change here, so this time slice is a 1. No change here, this time slice is a 0. Have a phase change here, it's a 1, and another phase change there, so it's a 1. Okay? So that is how we modulate using phase. And as I said earlier, 802.11n uses a combination of phase and amplitude modulation to get those speeds up. Okay? So basically we have our digital data and our analog carrier wave, and this is what our modulated signal looks like. And for extra credit, what type of modulation are we using? Frequency. All right, excellent, very good. All right, now we know that when we send radio waves out, they're not going to go forever. Just through the natural law of physics, free space path loss, okay, the signal's just going to get weaker as it travels forward. Okay, but there's also some things about the propagation or the way that that wave moves while it's traveling that will introduce loss or attenuation of that signal. Okay, 5 items here. Again, if you're going to teach wireless, you got to know this, and plus it's going to be on the CWNA exam. I guarantee it. Okay, reflection, refraction, scattering, diffraction, absorption. We just don't have the time today to go into all that stuff, but as a visual, this is what we see where we just got a straight signal goes from point A to point B, that's fine. In reality, there's just wireless signals flying all over the place. Bill's going to demonstrate that here in just a few minutes, okay? So this is nice and neat, but that ain't true, folks. That's not how it works. There's just radio waves flying all over the place. So some are going to be reflected, some absorbed, some are going to be broken apart into multiple pieces, and on and on and on and on and on. So when you're designing your wireless network, you need to consider all of these wave behaviors for when you place your access points in the ceiling. You just don't put them up there and hope for the best, which is what a lot of people do, unfortunately. Okay? On the flip side of loss, we have gain. Because if you know you're going to introduce loss, either naturally or through those 5 behaviors, you may want to boost your signal a little bit to get some gain to make sure the signal gets to the other side. Okay? 2 types of gain. We have active gain, where you physically boost the signal. And then we have passive gain, where you can switch to a different type of antenna or using the antenna itself to add gain into that signal. And again, we don't have the time to go into all the physics, but real quick, 2 things you need to know. Power, all right, is a constant measure measured in milliwatts. Okay? So let's say that you may put 400 milliwatts of power into that antenna. It's going to create a radio wave that's going to be gained or stronger than if you did not boost that signal by that much. Okay? And if you boost your signal up to 4 watts of power, the men in black from the FCC is going to come knocking on your door, because that's the FCC regulation. If you broadcast a radio signal greater than 4 watts or 4,000 milliwatts, the FCC considers you to be running a radio station, and they're going to make you buy a license. Okay? So keep that in mind as you're setting up your power setting. All right, so active and passive gain. Continuing on with antennas, 3 different types. We have omnidirectional, semi-directional, and highly directional antenna. Different types, different characteristics. Again, due to the time, can't get too much into that, but as you can see, here's a couple of examples. We have an indoor dipole antenna, which I'm sure everyone's used to, and this is an outdoor omnidirectional rod antenna. All right, omnidirectional means that what you do is you're sending electricity vertically, which means you are going to get a horizontal signal like this, because those two run perpendicular of each other. So if you were to turn your antenna down, and I've seen so many people do this, they put one antenna like this and one antenna like this and think they're going to get better coverage. And I see all the engineers laughing. Ha, yes, I know, I agree. What'll happen is your radio wave here will go this way, and this one will go this way, and what's going to happen? They're going to collide, and you're just not going to get any increase in power. Anyway, those are dipole and rod. And here's some examples of semi-directional, the Yagi, the patch, and the panel. And then we have the parabola, the dish, where we get a very highly focused signal. You'll see those dishes on top of towers and stuff like that. All right, so we've got the data. We're ready to transfer it, or excuse me, to transmit it. How are we going to do that? We all know about, for those of us that teach Ethernet or have done it, where we have the packets of data, the data is broken down to packets, blah, 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 blah. Well, before that packet can be transmitted, it has to be put inside of what is called a frame. You have to frame the data to prepare it for transmission. When you want to ship something, you just go to the FedEx office and drop it on the counter and say, here, ship this. No, well you can, but you're going to pay extra for it. They have to put it inside of a shipping container. Wireless networks are all networks are the same way, wired or wireless. That data's got to be framed up to get it ready to be transmitted to where it needs to go, okay? But the frame types are different between a wired and a wireless network, and even between the wireless standards themselves. The frame types are different, okay? And again, are they compatible? Yeah, kind of, sort of, but not really. Now, when you're talking about framing up data, we have to refer to our old friend, the OSI model. Everybody loves the OSI model, right? Okay? With a wired or wireless network, it doesn't matter. From the network layer up, wired wireless networks are exactly the same. The way that data is prepared for transmission. However, in the lower 2 layers, data link and physical, that's where things get a little bit different. Because the wired network handles it differently than a wireless network, and a B handles it differently than A, which handles it differently than G, and on and on and on and on and on. And if you want to take the CWNA test, you got to know the difference between all of those different frame types, okay? As you may know as well, the data link layer is subdivided into 2 smaller layers, or 2 sublayers, okay? And the physical layer is also subdivided into 2 sublayers as well, all right? And each sublayer performs a different function. Again, we just don't have time to go through all that. All right, but basically your packets come down, and at this point they're called data units. That's what that DU stands for, okay? So those data units come down, they're framed up, where it's put in the frame, at the data link layer, at the physical layer, that is where those data frames then are converted to real ones and zeros, and then transmitted either out on the wire or into the air. Something 802.11n can do, lots of little things that make 802.11n faster, is what it can do is called aggregate frames, okay, which is what the A stands for. So we have all these different segments or data units coming down. 802.11n can package multiple data units into a single frame, and then take these 2 frames and put it into just one bigger frame. So that's one way the 802.11n can speed things up. All right, 3 different types of frames, and we're all done talking about frames. Yay, okay? Management frames, used to manage access to the wireless network, associations, and all that type of stuff. Control frames assist with the delivery of the data, and then data frames, of course, are the actual data that is being transmitted. Just like there's 3 separate bus lines on the motherboard, you've got 3 different types of frames to help manage everything that's going on your wireless network. Okay, service set. What is a service set? Yeah, it's your wireless network, okay? All right, it is all the devices associated with your 802.11n wireless LAN. 3 different types of service set configurations. Test question. Basic service set, extended service set, and your independent basic service set. All right, basic service set, 1 access point, 1 or more client stations, also called test question. Infrastructure mode, all right, which is what everybody has in there. Everybody's got a wireless network at home, right? Okay, all right. So you have one access point probably, unless you're Bill, and you got, what, 3 or 4? 3. Okay, all right. And anyway, so that's one. And then the name of your network, that is your SSID, similar to a Windows workgroup name, all right? Here's a couple of graphics to go with that, okay? So we have the basic service at one access point, multiple client devices, and then we have the basic service area. Again, you've got an omnidirectional antenna. Theoretically, you get the perfect circle coming from that, but in reality, it's just going to be a jumbled mess, all right? You may get good coverage over there and not over there, and you have to figure all that stuff out when you do your site survey, okay? Extended service set, it is the same SSID or the same network name, but we have multiple access points associated with that network. And so then, of course, we can have seamless roaming from access point 1 to access point 2. All right? And then an independent basic service set is just client devices just talking to each other without an access point, and that is called a peer-to-peer or ad hoc mode of wireless networking. All right, now, so we know the basics of how we're going to transmit all this data, but how do we get the client device onto the wireless network? So at the MAC layer, or sublayer, 4 functions that it has. It discovers your wireless network, or a wireless network, joins the network, then it can start transmitting, but then it has to remain connected. All right, now all that happens at the MAC sublayer in there. So what the client device has to do is scan for a network to attach to. Okay, by and large, it's probably going to do what is called passive scanning. All right, where wireless devices listen for a beacon frame, okay, from an access point. By default, your access point will send out what are called beacon frames. Here I am, here's my name, attached to me. So when you go into Windows, you want to view wireless networks in the area, it is picking up the beacon frames from all the access points that are in the area. That's how you get that list of names, through the beacon frame, okay? That's passive scanning. The client's just listening for something to attach to. Active scanning, on the other hand, is when the client sends out a beacon frame of its own saying, hey, is anybody out there? I want to connect. All right? So what Bill could probably do is, if he's trying to find networks that he can break into, he is going to do active scanning to try and find an unprotected network somewhere. But by and large, passive scanning is the way that clients then attach to the wireless network, and the difference between the two is which device initiates the discovery, the client or the access point. All right, so we found the network. So what we need to do now, or what the client needs to do, is authenticate and associate to that wireless network. Test question. A client must authenticate before it can associate. What we're going to see here in just a minute is that a client authenticates to the network, but it associates with the access point. Okay, so kind of keep that in mind as we go through this. Okay, so 2 types of authentication were defined in the original standard. Open system authentication, okay, where the client device is just listening, it found a network, and then it basically sends a frame to the access point saying, hey, can I sign up, can I join your network? The access point says, sure, come on in, and boom, you're attached. Okay, so no real authentication really takes place. All right, it's just come on in and join the party. That's pretty much how that goes. Now on the other side of that, we have what is called shared key authentication, where the client device must get permission from the access point to join the network. Who had to type in HI-TEC 13 to get on the network? And people had to do it like every hour because you kept losing your connection. Okay? All right? So this would be an example of a shared key authentication, HI-TEC 13. You got to type in the code to get access to the network. You're not authenticating to the access point, you're authenticating to the network. Okay? All right? So we've authenticated, now we associate to the access point, where the access point then will read the client's MAC address, add it to the OK list, and then you're off to the race and you can open up a web browser and all that type of stuff. Now, as you move around or roam, test question, from one access point to another, what you need to do then is disassociate from your current access point and reassociate with the new access point. Okay? Now, once a station has been authenticated and the network IDs are the same, you do not have to re-authenticate again, because you authenticate to what? The network, not to the access point. Okay? So when you roam, all right, and you find another access point, the client then is going to reassociate with that new access point. Okay? However, the connection has to be broken between the new access point, or between the client and the old access point. That is handled by the new access point. So a client then will reassociate to a new access point, and then the new access point will disassociate from the old access point. So, test question, reassociation is initiated by the client or the station. Disassociation is handled by the access point. So the connectivity process, one, a device will scan for wireless networks, chooses an access point, authenticates, associates, gets an IP address, and then you're off to the races, okay? So you're connected to the network. Now, how are you going to transmit data? Everybody knows about CSMA CD, right? Okay, can we use CD on a wireless network? What does CD stand for? Collision detection. Can a wireless device detect a collision? No, there's no way. It just sends its data out and hopes for the best. Okay? So DCF is distributed coordination function. Okay? So all of the devices then have to share the responsibility of transmitting in a polite, orderly manner so nobody gets all tangled up. Okay? So it does that wirelessly through something called virtual carrier sense, where each client on the network is assigned a number called the slot time. Okay? And then your timer's got to count down to 0, and then it's your turn to transmit on the network. Okay, is how that works. Just remember the DMV. You get in line, you pull a number, you wait, you wait, you wait. They call your number, you get to the front, you do your business with the agent, you're all done and you go. However, if you're not done yet, you got to take another number, go to the back of the line, and start all over again. Now, on the next one, the mortal enemy of performance is retransmission of those data frames. Okay? So let's say I want to communicate with Bill. Take a number. I get in line. I finally get my turn. I get to the front of the line. I send Bill my data, and Ethernet standard says the receiver has to do what? Send an acknowledgement. So I come up to the front of the line. I send Bill my data. Remember those time slices we saw earlier? That's all you get. Okay, you get your slot time, and that's it. When that time is gone, guess what happens? You go back to the end of the line. So I'm at the front, I send Bill my data, and it's like, Bill, my time's almost up, man. Okay, come on. Bill doesn't send the acknowledgement, what happens?
I'm at the bar, by the way.
Yeah, that's right. I have to go to the back of the line, and what do I have to do? I have to retransmit the data I just transmitted before, but because I did not get the acknowledgement, I have to keep retransmitting that same data again and again and again until Bill sends me that acknowledgement. Okay? So retransmissions is bad. Also, the number of clients per access point. Is that because then the line gets longer before you get your chance to get to the front of the line to transmit. So again, this is crucial when you're doing your site survey and placing your access points. You know, you got 50 people on this one and 10 people on this one. Who's going to get faster service? Well, with only 10, because the line isn't as long. Okay, so that's one thing you want to think about when you're placing your access points. Another thing 802.11n can do is block acknowledgement. Because I can send Bill, remember we were putting multiple frames inside the aggregate frame? I send Bill the aggregate frame, okay, with multiple frames in it. I only have to get one acknowledgement for that aggregate frame. I don't need to get a whole bunch of acknowledgements for everything that was packaged inside. So that's another way 802.11n can help speed things up. Okay? A couple of specialized tools. First one is called a spectrum analyzer. When you're doing your site survey to place your access points, again, you just don't haphazardly hang them on the ceiling and hope for the best. Okay? Not that we've all worked in environments like that before. Okay? But you really need to go out there and see what type of wireless traffic is already in existence out there, or dead zones or things like that, before you hang up that access point. So what you're going to do is use a spectrum analyzer, okay, which looks something like this. We have one. Bill's going to put one on the screen here in just a couple of minutes. But it shows you the wireless traffic that's in the area. That's what a spectrum analyzer will do. Now, another tool is what is called a protocol analyzer, which not only can you see the traffic, you can actually open up those frames, open up those packets, and read the data that's bouncing around in the room. All right, so this is an example of Wireshark. Bill's going to show that here in just a couple of minutes. So, Bill's going to take over at this point and talk a little bit about security.
And one of the things that you always hear, in fact, one of the things I always teach my students is that wired is preferable to wireless in most corporate situations, primarily, well, to some extent because of the speed issues, more importantly, the security issues. Wireless, by its very nature, has to be an insecure environment. You're basically transmitting packets through the air. So things are flying all over the place. So the good guys can hear it just as easily as the bad guys can hear it. So we have to be very cognizant of security when we're dealing with wireless environments. So always remember, wire where possible, wireless when necessary. So first of all, obviously, how do we secure is very important. You all know the 3 letters, CIA, and it's not that one, or NSA. By the way, they're recording all of this as well. So CIA, confidentiality, integrity, and availability. Those are the 3. As you're doing wireless, you have to even be more attentive to the detail on it. So 3 more terms that you need to know. We talked about authentication, authorization a little bit. So once again, just as a little brief, I always say authentication is who you are, verifying your identity, and that can be done using anything from passwords to biometrics to key cards. Authorization is once you've been granted authentication, you are who you say you are. Now we have to confirm, okay, you're Bill Saichek, what are you allowed to do? So my IT staff says Bill Saichek is allowed to do nothing. And that lasts about 30 seconds. And then Bill Saichek gets to do everything. But that's a whole nother story. And then accounting is what they do to figure out that I've hacked their network and I've given myself more permissions than I should. There are lots of ways of doing wireless network discovery. We have a little demo. In fact, why don't you pop it up right now?
Okay.
I don't know if anybody has ever seen this site. I just got shown when Karl and I were working on this. It's called Wigle, W-I-G-L-E.net. You can actually enter in an address, a location, or whatever, and it will show you all of the active access points. Now, there is probably some level of delay, so this may not be immediate, but it's close enough. We just put in the address of the hotel, and these are all the access points within about a 2-3 block radius.
And somewhere in there is Renaissance Guest and Renaissance Conference Room.
If we zoomed in and could figure out exactly where we are,
yeah, it would take
here's
5
the
minutes.
courtyard. I know
come
courtyard's right there.
Okay.
So we're probably somewhere in this cluster.
Yeah, but you will see there's like, I can't see it now. There is, and it's not on this map. We were seeing, these are SSIDs. We talked about that a few minutes ago, okay? On that map, you'll see SSIDs that just say Linksys or D-Link or Verizon or something similar to, and I see everybody starting to smile. Where am I going with this? If somebody didn't bother to change their SSID from the default, what do you think else they didn't change?
Security.
The password. So you could use this map, and not that I condone this, of course, okay? But you could use this map and find a Linksys hotspot, drive wherever it is, and chances are, if they didn't change the SSID, they may not have changed the password either, and then you know the rest of the story. And Sam's just sitting there, it's like, yeah, that's kid stuff, man.
Yeah, that's like, you know. And of course, you know, there are about 75,000 applications. Most of you probably have seen or heard of NetStumbler.
Yep.
You know, freebie application, runs on Windows. I think there's a Mac version, but don't.
It's not maintained very well.
Oh, okay. But definitely the Windows version. You can definitely throw that on a laptop and just war drive around your neighborhood and find out all the open access points that somebody forgot to set security on. Cool. Okay. So again, other things that can happen within an organization, and this is something that most students don't learn about until they're actually in that position. And that is, if you are working for a company or you have a company that you're doing work with, and they don't want to grant you wireless access, or they don't make it easy for you to get wireless access, what's the big deal about simply taking a $30 AP that you bought at Fry's or Best Buy and simply plug it into the wired network, and now you have your own rogue network? So a lot of organizations are now starting to have to fight that. And a lot of it is, how do you detect them? So that's, again, coming back from the other side. And then there's the other way to do it is you can sometimes get in because they'll say, well, we're only going to allow these particular pieces of hardware because we're going to record the MAC address. No big deal. You figure out what MAC address, and you do that by just sucking some packets off the wires or out of the air. And the next thing you know, you say, oh, that one, I can simply have that be my reported MAC address. And the AP is, okay, that's got the right address, and in you go. Denial of service attack, it's a great way to do it. You can really jam up a wireless network by just throwing in a high flood of traffic. You can hijack the network. A lot of things that can be used to exploit security feature weaknesses if we'll talk about WEP in a second, but social engineering, you know, call up somebody and say, hey, I would like to get onto your wireless network. It's Fred in accounting. Oh yeah, Fred, the passphrase is XYZ2749 or whatever it happens to be. Remote administration, if you can figure out how to come in through the back door, through the wire side, you can maybe hack the access point and figure out what all the information is on the other side. Eavesdropping, we talked about war driving with utilities like NetStumbler, man-in-the-middle attack, evil twin. These are all of the very common attacks that you can do to hack through wireless
Okay, a couple things I want to add real quick.
Please.
When we were talking about when you have your slot time and you get to go to the front of the line, part of the frame is the amount of time you're allowed to stand at the front of the line to get your turn. What Bill could do, not that he's ever done it, I'm sure Sam might have, we'll see. But anyway, what you can do is inject a frame in there so that your slot time doesn't expire. So if you get to the front of the line and your slot time doesn't expire, how much time are you going to get at the front of the line and what's going to happen to the people behind you? Okay, so that's one way. And the evil twin, I'm going to pick on Sam here again. What if Sam set up his laptop to be an access point with an SSID of Renaissance Guest? And you go there, you attach to Renaissance Guest, guess what you're really attaching to? You're attaching to Sam's computer, and guess what Sam's going to do with all the packets you're sending to him? Okay?
Okay, so obviously 802.11 was never really designed, like much of the OSI model protocols, with security in mind. It was designed for actually more open access. So there was very, very little security built in. The three that they kind of created, that everybody adopted, was basically hiding the SSID, you know, not broadcast it, in other words. Number two is to filter your MAC. I mentioned that is you simply put a list of the MAC addresses that are allowed to associate. And then they did have a sort of what they thought was pretty cool encryption technique called WEP. So it was not a very, none of the three were very good. And we'll talk about that on the next slide. So first of all, SSID hiding. A lot of people, anybody turn off SSID broadcast on their own home wireless? Okay. It's a nice way to keep your neighbors, you know, kind of the unwashed masses from finding out your network. It doesn't hide your network against somebody who's really wants to find it. Even though it's hidden, it's still there, even though you associate. And in fact, something interesting, if you're hiding your SSID, a client who has attached to it before, like your laptop, it's going to send out, you know, hi, I'm Bill's Wi-Fi. But if Bill's Wi-Fi's SSID is turned off, your laptop is saying, hi, is Bill's Wi-Fi out there? So it's going to send it back. The name is going to be somewhere. So it's not a horrible thing to do. It does give you some obfuscation, but on the other hand, it's not the best realm of security.
Yeah, and the thing is too, if you disable your SSID broadcast, how are you going to roam from one access point to another? You can't.
It makes roaming very difficult.
Yeah, it makes it really tough. All right.
MAC address filtering I mentioned before, easy to spoof simply because once you're sending packets, you figure out which ones are allowed, and there are tons of tools out there that you can get, and you basically inject your the desired MAC address into the frame. Yeah. And obviously, the authentication is where we're going as far as what WEP is concerned. Now, there's a few other things where you are not authenticating with your own personal ID and password. What you're doing is your device, your phone, your laptop, your pad, whatever it happens to be, is not actually associating by name, but it's associating by the device itself. So it's associating with its own name, its own MAC address, etc. So then you have a problem because since there's no inherent security at the device level, if it isn't added to in some other way, it provides a huge security hole. So open system authentication was the way they used. All you needed was an SSID to connect, and that was it. That was the basic elements. In fact, that was what they thought. All access points are going to be open everywhere. And there are no bad guys in the world, and we all have little fairy dust, and et cetera, et cetera. Now, eventually they said, well, this is dumb. So when WEP came along, when they brought WEP in as a semi-authentication method, what they did is you would have a shared key. You would set up a key on your access point. You would set up a matching key on your device, your laptop, pad, phone, whatever. Then the two would just, during the authentication process, this is what I'm looking for, this is what you're sending, cool, we have the same password, we're great. And that's why WEP sucks. Because the actual password can be sucked out of the IVs that are transmitting back and forth. If you're looking for a lab assignment, you know, in wireless and say, well, what can you do with, what kind of fun stuff you can do? This is a great one. You set it up very easily. You need a little bit of, you need a couple of special wireless devices just so that it can interface right. You use Backtrack, which is, or what was the other one you used?
Well, now it's calling background short.
Okay, but you use one of those packages, and now the race is on. I challenge my students when they do it, who can crack it the fastest? My record is 5 minutes and about 15 seconds for my students to crack 128-bit WEP. The implementation, WEP implementation, it commits the cardinal rule, it breaks the cardinal rule, simply that the actual password can be derived from what's being transmitted, as opposed to using a hash value or some kind of a token, if you want to think about it.
And when the transmission does take place, the initialization vector is attached to that frame, and the data may be encrypted, but the initialization vector is not. Oops, who thought of that one? Okay, yeah. So then and it's only a 24-bit number. So what happened there? That is a finite number. Okay, and at some point you have to start reusing those numbers again. So that's where the pattern comes in at, because eventually you just got to use them and use it again and again and again. Also, it uses WEP uses what is called the RC4 cipher. If you've had some security classes, you'll know that. It's a stream cipher, and it sort of produces a random number, but not really. Okay, so between the IV and the RC4 cipher, WEP is just crap.
The methodology right now that is considered one of the better ones, especially in a less than secure environment like a home environment, would be using WPA, Wi-Fi protected access. It was a much better security encryptions, work much better. It's intended for it's intended for both the personal user, there's WPA at the personal level, and at the enterprise level. It uses TKIP, Temporal Key Integrity Protocol. It is still a shared key, but it's not really a key, it's more of a passphrase. But the actual key is never really transmitted. Mm-hmm. The keys generate a kind of a cipher, and then the ciphers go back and forth, and those ciphers change mathematically at a specific interval, which you can define. WPA2, introduced in September of 2004. It's based on the 802.11i standard. It does have some backwards compatibility with WPA, which does mean that you can, in some cases, intersperse. So you can have some of your clients with WPA and others with WPA2. If you can run WPA2, you're doing much better. It addresses both encryption and authentication, so it takes care of both sides, which is really nice. You can use TKIP with WPA2, but much better to use AES, which is a great algorithm for encryption.
That's on the next slide, yeah.
Yeah, go ahead.
Okay.
Authentication is accomplished using 802.1x. One of the things you can really get away with is using radius servers. Now, radius servers are really cool because now what you're doing is you're actually adding username and password capability on the backside, where yes, you can associate with an AP, but you ain't getting in until you validate who you are. But it's not the device. You actually can validate to the actual individual.
And whereas, so encryption, then they got rid of RC4, they replaced that with AES, and as far as I know, Sam, help me on this one, AES has never been cracked, is that correct?
Yeah.
Okay. And also, if you want to do 802.1x, this is what, and this is a test question, by the way, on the exam, is if you want to set up what is called a robust security network, then you have to run WPA2 enterprise level. If you're going to do WPA2 personal, you use the pre-shared key. If you're going to do WPA2 enterprise level, you got to have a radius server, okay? And AES is a block cipher, not the string cipher. You see the difference there between the two. That'd be harder to crack a block of data than it would be just individual characters, okay?
Okay, so authentication, 802.1x, which is WPA2 to most extent, requires an authentication server, again, radius in the backside. A lot of the controllers today If you get with the wireless controllers, they have the radius server built in. You can actually leverage Windows Server 2000 and I believe 8, I know 10 or 12 does. They actually have a radius server that you can use on the back end if you want. You can build a radius server out of a Linux box for free. A lot of ways to get your radius on the backside. Some of the tools you can use to protect a LAN, one of the things is I always tell my clients when I still do some consulting, is we are going to set up a VPN. You want to connect to the network, VPN, because what you do is you establish your virtual network, which is encrypted, highly encrypted, between your device and the edge of your corporate or home network. Now, it doesn't matter if you're on a wide open network at a hotel, all of your packets are going through its individual VLAN, or its individual VPN. There are wireless intrusion detection systems out there as well, and there is both detection and prevention. I'm going to
Okay, well,
need to
that's,
speed up.
yeah,
I'm
and
sorry.
the difference between the two?
Oh, detection is, are you trying to break in? Prevention is, I'm going to stop you. It's easier to, by the way, it's always easier to prevent something than it is to detect it, to some extent. And it's, both of those are a hell of a lot easier than trying to correct it once it's screwed up.
Yeah.
So you start with prevention, add detection as a secondary, and then hopefully you won't have to worry too much
Okay.
about
Just
fixing.
on a side note, when in our wireless class, when we got some new wireless equipment, and it was enterprise level stuff, and the first time that we connected it to the college network, what do you think happened? Yeah, that's what happened, okay? The intrusion prevention system at the college shut off all the ports in the classroom, instantly. And our equipment just stopped working. We couldn't use it at all. And it took us like 2 weeks to figure out what was going on. Okay, so we had to have the IT guys come in and set us up a separate subnet and blah, 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 and all that kind of stuff. So intrusion prevention does work, okay? The one thing I'd mention that if you're really gonna do that and you're serious about it, don't make your client access points do double duty as your intrusion prevention and detection system. You're gonna have a separate set of access points to cover your network and a net to detect the rogue access point and somebody trying to break in.
Okay, so quick summary. Number one, know that SSID hiding and MAC filtering are completely ineffective, although the hiding might just be something you want to do just to keep yourself a little bit in the background. WEP should never be used. It says here, in any production, business, or home network, underline, boldface, capital letters. Never ever use WEP. WPA does have some security weaknesses, but for the most part, it's probably safe enough for a home environment, although I would be suspicious of using it in an enterprise or corporate environment. And then make sure you disable any and all remote administration, which means you should never be able to access the management console of an access point or a controller from the outside of the network. Now, that contradicts what was said earlier, but in that case, you have a VPN, you come in through the back way. So nearly 80% of all network security breaches come from inside the organization.
And it's not always
Interesting.
intentional either.
No. I mean, anything from rogue access points to somebody has a misconfigured card. Or you come in with some weird device that just keeps, just blows everything off. Weak passwords are, of course, going to be a serious security threat. That's Security 101. And obviously, you can have the strongest security, but it can be broken with the weakest link.
And of course, the weakest link is
Your people.
the users.
Okay.
Okay, so what's next? 60 years ago, video was delivered via broadcast television. Okay? All right, in the 1980s, video shifted to satellite and cable. Today, the internet streams music, movies, TV on demand, and all that stuff. Quick survey, I asked this in class as well. Does anybody do appointment television anymore? For example, Criminal Minds comes on at 9 o'clock on Wednesdays. Does anybody camp out in front of the TV at 9 o'clock on Wednesdays anymore to watch that show? If you watch Criminal Minds, or any show, for example. Okay. Nobody. Everybody's got DVRs, right? And all that other, and Hulu and all that other kind of stuff. Estimated global traffic will reach nearly 1 zettabyte. 90% of that will be video content. All right, so that is going to say with 802.11ac coming, and they're already talking about the replacement for 802.11ac already even. Well, our J45 connections go the same way as 8-tracks and vinyl records. If you youngsters don't know what 8-tracks are, ask your mom, okay? All right? So, final word, 802.11ac is going to be a game changer. If you want to future-proof your wireless networks, find the 802.11ac specs, set your wireless networks up to follow those 802.11ac specifications. Because like I said, 802.11g is going to be obsolete within just a few more years, okay? All right, and I think that's all we have on this. Questions on anything before Bill goes into the lab piece? All right, well, thank you very much. Bill, I'm going to turn it over to you.